Boil, expand, condense, repeat. The Rankine cycle in action. Part 1 is an episode of the Degrees of Freedom Project videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. These videos, Boil, Expand, Condense, Repeat, the Rankine cycle in action, Part 1 and Part 2, describe the Rankine cycle, which is the basic steam power plant cycle behind most of the large electrical generating facilities, whether it be powered by coal, natural gas, or nuclear energy in the United States and throughout the world. Part 1 describes the ideal version of the cycle with isentropic components for the turbine and for the pump. Part 2 describes modifying the ideal cycle to account for real behavior in an actual cycle, and demonstrates using DWSim to model both versions. We'll begin by reviewing the Carnot steam cycle that we saw in Sadie Carnot in The Power of Fire, the 1824 edition video. We have a boiler, a turbine, a condenser, and a pump. And on the Carnot steam cycle, we started at state B and did an isothermal transition in the boiler, an isentropic expansion in the two-phase region in the turbine, an isothermal condensation, and then an isentropic pumping or compression of the partially condensed steam to return to state B at the input to the boiler. Just to review our previous results, the thermal efficiency was 1 minus T cold over T hot, which worked out to be 21.13%. We had earlier derived the same result by analyzing every step. Also, the network was 410 kilojoules per kilogram. The Q hot was 1939.8 kilojoules per kilogram, and the Q cold was minus 1529.8 kilojoules per kilogram. Here is the spreadsheet summarizing the Carnot cycle. The original spreadsheet is linked on the webpage in the description. So what are the engineering problems with the steam Carnot cycle? Well, one problem is that the turbine operates largely in the two-phase region. Why is that a problem? Well, tiny water droplets at high temperatures tend to erode metal turbine blades very badly, and the lower the quality of the steam, the worse the erosion is. You don't want to have to be replacing your turbine blades every few months. It's very expensive. Another engineering problem is, as we mentioned before, it is an awful lot of work to compress a vapor or a gas, and compressing a two-phase mixture is just really challenging. We have to fix both of those two problems, and to do so, we're going to look at the Rankine cycle. Here are the TS phase diagram and the process flowsheet diagram for the Rankine cycle. The Carnot cycle from our previous example follows the dashed lines on the phase diagram. In the process flow diagram, we have the same components: the boiler, the turbine, the condenser, and the pump. However, the process from B to C is now isobaric instead of isothermal. The steam is now fully condensed into liquid water at point A. So now, the pump is only pumping liquid, which means it will use much less power and will survive much longer than a two-phase compressor. Delta H for the pump is V delta P. In addition, we have superheated the steam beyond the two-phase region, so that when it condenses and passes through the turbine, we are much closer to the edge of the two-phase region and have higher quality, which means that the erosion of the turbine blades will be much less. We will now calculate a Rankine cycle example for a steam power plant that operates with steam entering the turbine at 80 bar and 500 degrees Celsius. The condenser operates at a temperature of 44 degrees Celsius. We're going to calculate the thermal efficiency of the cycle. And we are also going to calculate the water circulation rate for a net power generation of 80,000 kilowatts, which is a medium-sized generating facility. First of all, we will need data from the steam tables. At 44 degrees Celsius and 0.091118 bar, we will look up H hat of the liquid, H hat of the vapor, S hat of the liquid, S hat of the vapor, and the specific volume of the liquid. At 500 degrees Celsius and 80 bar, we will look up H hat and S hat. At 44 degrees Celsius and 0.091118 bar, we have the V hat of the liquid is 0.001 and change cubic meters per kilogram. H hat of the liquid is 184.26 kilojoules per kilogram. H hat of the vapor is 2580.7 kilojoules per kilogram. The S hat of the liquid is 0.62547 kilojoules per kilogram Kelvin. And the S hat of the vapor is 8.1816 kilojoules per kilogram Kelvin. At 500 degrees Celsius and 80 bar in the superheated region, we have that H hat is 3399.4 kilojoules per kilogram, and S hat is 6.7264 kilojoules per kilogram Kelvin. We'll start at point A and calculate the work in the pump. First of all, as we did in the Entropy Made Me Do It, pumps, nozzles, and the other second law shenanigans video, we see that the work rate over m dot is delta H hat, and that's what's going to be V hat delta P, which is why we looked up V hat of the liquid. So we have 0.001 cubic meters per kilogram times the delta P, which is 8,000 kilopascals minus 9.1118 kilopascals, that comes out to 8.067 kilojoules per kilogram. So that means the H hat B is going to be the H hat A plus delta H hat. So that's 184.26 plus 8.067. So that's 192.3 kilojoules per kilogram at point B. Next, we analyze the boiler. For the boiler, delta H hat equals Q dot over M dot equals H hat C minus H hat B. And from the things that we've looked up or calculated, that's 3399.4 minus 192.3, or 3207.1 kilojoule per kilogram. Next, we will analyze the turbine. Since we're doing the isentropic calculation, we don't have to worry about the turbine efficiency at this point. So the shaft work is equal to delta H hat. We're going to assume the turbine is isentropic, so delta S hat equals 0, which means that S hat C equals S hat D. As we've done before, you can calculate the quality from the actual entropy in the liquid and vapor entropies. That gives us the quality at point D is 0.8074, or 80.7% steam. Now that we have the quality, we can calculate the enthalpy. H hat D is equal to the quality times the vapor enthalpy plus 1 minus the quality times the liquid enthalpy, or the quality times the enthalpy of evaporation plus the liquid enthalpy. Plugging in those values, you get 2119.2 kilojoule per kilogram as the enthalpy at point D. That gives us a delta H of 2119.2 minus 3399.4, or minus 1280.2 kilojoule per kilogram. That is also the work generated by the turbine. Again, the negative sign is because the work is coming out of the turbine. Now we can calculate the efficiency for the process, and that's the net work over Q hot, and from the numbers we've already calculated, that's 1280.2 minus 8.067 over 3207.1, which works out to 39.7%, which is a pretty decent efficiency. Then, we can calculate the flow rate of the water through the system. The net work is 80,000 kilojoules per second, which is equal to m dot times the net work. Solving, m dot equals the net work over the specific network, or 80,000, over 1280.2 minus 8.067, which works out to 62.88 kilograms per second. That's a pretty healthy flow rate of water through a system. Here's the spreadsheet summarizing the ideal Rankine cycle. As usual, the problem parameters are in green, the reference values, such as the steam table values, are in blue, and the answers are bolded. The rest of the layout should be fairly self-explanatory. The original spreadsheet is linked on the web page in the description. In Boil, Expand, Condense, Repeat, the Rankine cycle in action part 2, we will look at a realistic Rankine cycle and show how to use DWSim to simulate both a real and an ideal Rankine cycle. The takeaways from this video are 1. The ideal Rankine cycle modifies the steam Carnot cycle by fully condensing the water, pumping it, and replacing the isothermal boiler with an isobaric boiler. 2. Compared to the Carnot cycle, the ideal Rankine cycle has a reduced thermal efficiency, but an increased lifetime for the pump and the turbine. And 3. As with all power cycles, the thermal efficiency is the net work over Q hot. Thanks for watching. This video was brought to you by the DOFPro team.